What is TypeScript? TypeScript is a programming language developed and maintained by Microsoft. It is a superset of JavaScript, which means any valid JavaScript code is also TypeScript code. The main additional feature TypeScript offers is a type system that provides stronger type checking at compile time, which can lead to better software reliability and maintainability. TypeScript is designed to develop large applications and compiles to JavaScript. Now, let's look at a simple example to demonstrate TypeScript's type annotation feature. In the provided code snippet, the variable message is declared with a type annotation, string, which signifies that the message variable should always hold a string. TypeScript will check this at compile time and throw an error if any assignment is made to message that is not a string. The console.log statement then outputs the value of message to the console. When this TypeScript code is compiled, it generates JavaScript code that the browser can execute. Why TypeScript? TypeScript is a superset of JavaScript that compiles down to plain JavaScript. It offers additional features that aren't available in the regular JavaScript, such as strong typing, interfaces, and compile time error checking, which can help developers catch errors early in the development process. In the code, the variable message is of type string, a feature not available in plain JavaScript. This type annotation helps ensure that message will always be a string, and if we try to assign a non-string value to it, TypeScript will generate a compile time error. This early error detection adds robustness to the code. Setting up the development environment. Before we start writing TypeScript, we need to set up a development environment that can compile TypeScript code into JavaScript, since browsers and Node.js execute JavaScript code, not TypeScript. This command installs TypeScript globally on your machine using Node.js Package Manager, NPM. Having TypeScript installed globally allows you to use the TypeScript compiler, TSC, from any directory in your command shell to compile your .ts files into .js files. Compiling TypeScript to JavaScript. TypeScript is a superset of JavaScript that adds type information to your code. Before it can be executed in a JavaScript environment, TypeScript code must be transformed to plain JavaScript. This process is known as compilation or transpilation. This command runs the TypeScript compiler TSC, which takes a TypeScript file, in this case hello.ts, and compiles it to a JavaScript file hello.js. By default, the output JavaScript file will have the same name as the TypeScript file and will be in the same directory. Basic TypeScript workflow. TypeScript is a typed superset of JavaScript that compiles to plain JavaScript. It offers static typing, classes, and interface. To start using TypeScript, you need to set up your development environment, write your TypeScript TS code, compile it to JavaScript.js, and then run the JS in your environment. Firstly, you install TypeScript globally using npm Node.js's package manager. Then you write your TS code in a file, like helloworld.ts. Using the TypeScript compiler TSC, you compile your TS file to a JS file, helloworld.js. You can then execute this JS file using Node.js or in the browser. tsconfig.json configuration. The tsconfig.json file specifies the root files and the compiler options required to compile a TypeScript project. It serves as a configuration file for the TypeScript compiler. Here is a basic example of a tsconfig.json. In this example, compiler options sets up various options for the compiler. Target specifies the ECMAScript target version, here ES5. Module sets the module system, CommonJS in this case. Strict enables all strict type checking options, and outdir defines the folder to output the compiled JavaScript files. The include property lists the files or patterns to include in the compilation. In this example, all TypeScript files in the src folder. Variables and data types. In TypeScript, variables are containers for storing data values. TypeScript is a superset of JavaScript, which means it contains all JavaScript's features enhanced with typing capabilities. TypeScript allows you to define the type of a variable, such as numbers, strings, or booleans, among others. Doing so can prevent bugs and make code easier to understand. In the code snippet, 3 variables are declared with specific types using TypeScript's type annotations. The variable message is of type string, which means it's expected to hold a text. The variable count is of type number, designed for numerical values, whether they are integers or floats. Lastly, isDone is a Boolean meant for true-false values. Type annotations in TypeScript are optional but recommended as they enable the TypeScript compiler to check for type correctness at compile time. Type annotations and inference. Type annotations in TypeScript are used to explicitly specify the type of variables, function parameters, return values, etc. They help catch errors during development by enforcing type constraints. The code snippet above declares a variable message with a type annotation string, indicating that the variable should hold a string value. The variable is then assigned the string "Hello TypeScript." TypeScript will enforce that message always contains a string, preventing assignment of values of other types. Functions and parameters. In TypeScript, functions are used to encapsulate reusable pieces of code. They can take parameters, which are typed, providing additional safety and clarity. TypeScript enhances functions with type annotations and return type annotations, improving the reliability of your code. The function greet takes a parameter name of type string and returns a string. The return type is specified after the parameter list before the function body starts. When the function is called with a string argument, it concatenates hello with the name and an exclamation mark to form a greeting. Objects and interfaces. In TypeScript, objects are collections of key-value pairs, where the key is a string and the value can be any type. Interfaces are custom types that you can define to describe the shape and types of an object's properties. They are used for type checking whether an object fits a certain structure. The provided code defines an interface user that describes an object with a number type ID and a string type name. The function getUser returns an object that fits the user interface. We can then safely access the ID and name properties on user because TypeScript knows the structure of a user. Arrays and tuples. In TypeScript, arrays can be defined in two ways. The first is using the type syntax, where type is the data type of the array's elements. The second is through array type generic type. In the provided code, fruits is an array of strings, while prime numbers is an array of numbers. We have assigned an array of fruits to fruits and an array of the first few prime numbers to prime numbers. TypeScript ensures that only strings can be used in the fruits array and only numbers in prime numbers. Enums. In TypeScript, enums are a way to organize a collection of related values. They can be numeric or string-based and give a friendly name to a set of numeric values. Let's explore a simple example of a numeric enum that represents the days of the week. In the code provided, we declare an enum named day, which represents the days of the week. By default, enums begin numbering their members at 0, so Sunday is 0, Monday is 1, and so on. Later, we declare a variable dayoff of type day and assign it the value day.sunday. When console.log dayoff is called, it will output 0, as that is the value corresponding to Sunday in the enum. Type aliasing. Type aliasing in TypeScript allows you to create a new name for an existing type. Think of it like a nickname or a shorthand that you can use to refer to a type, which can be a primitive, an object, or a combination of types with unions or intersections. It makes complex types easier to manage and your code more readable. In this code, typePoint is an alias for an object type with properties x and y of type number. We then declare a variable chord with the type point, assigning an object that conforms to the shape of point. This aliasing helps us not to repeat the object structure every time we need to refer to this kind of object in our code, thus promoting reusability and maintainability. Union types. In TypeScript, a union type is a powerful way to express a variable that can be one of several types. By using the pipe symbol between types, we can declare a union type which allows for the flexibility of variables to hold more than one type. In the code snippet, the function printID accepts a parameter ID that can be either a number or a string due to the union type number string. Inside the function, we're using a typeguard type of ID = string to check whether ID is a string. If it's a string, we convert it to uppercase. If it's a number, we print it directly. This demonstrates the use of union types to handle multiple types in a type-safe way. Intersection types. Intersection types are a powerful way to combine multiple types into one. This is done using the and operator, which signifies that a type should be all of the types it is combining. It allows you to build up complex types by combining simple ones. In the code provided, two object types, employee and person, are combined to create a new type, employee-person, using intersection. An instance of employee-person must therefore have all the properties from both employee and person. The variable worker is an example of this combined type and includes properties employee ID and start date from employee, as well as name and age from person. Type guards and differentiating types. In TypeScript, type guards are a technique that determines the specific type of a variable within a scope. They're especially useful when we work with union types or when trying to differentiate between types that could be assigned to a common variable. By using type guards, you can inform TypeScript's type system about the specific type a variable is, depending on some condition, hence making it safe to access the unique properties and methods of that specific type. In the code, a custom type guard function isFish checks if pet has a swim method to differentiate if the pet is a fish, assuming the fish type has a swim method and the bird type has a fly method. This function returns a Boolean, but also has a return type predicate pet isFish, which tells TypeScript that the pet is of type fish whenever the function returns true. In the if block, TypeScript knows that pet must be a fish, so it allows us to call pet swim without any type errors. If the condition is false, TypeScript assumes that pet must be a bird, and thus pet.fly is allowed. Nullable types and optional chaining. In TypeScript, nullable types are those that can hold either a value of a specific type or null undefined. By default, the strict null checks option is enabled in TypeScript, which means that null and undefined are not in the domain of any type except for their own types and any, the top type. In the code, name can hold a string or null. Initially, it is null. It can be assigned a string later. Assigning undefined results in an error because undefined is not part of the type union string, null. Mapped types. Mapped types in TypeScript allow you to create new types by transforming existing types. You define a new type by specifying a set of keys and deriving associated values based on these keys. This can be useful for creating types that are versions of existing types, but with modifications, such as making all properties optional or read-only. In the given code example, we define a type permissions as a union of literal types read, write, and delete. Using mapped types, we then create a new type, access control. This type maps each permission in permissions to a Boolean value, indicating whether that permission is granted. So the access control type is equivalent to an object type with three properties, read, write, and delete, each of which is a Boolean. Conditional types. Conditional types in TypeScript allow us to define a type that can vary based on a condition defined by a type relationship. This feature is similar to ternary operations at the type level, which can be useful for creating types that depend on other types, such as generic types. In the given code, non-nullable is a conditional type that takes a type T. It checks if T is assignable to null or undefined, and if so, it resolves to never stray, effectively excluding null and undefined from the type T. If T is not assignable to null or undefined, the condition returns T as is, effectively ensuring that the resulting type cannot be null or undefined. Generics. Generics provide a way to create reusable components that work with a variety of types rather than a single one. This allows users to consume these components and use their own types. In the code, identity is a generic function denoted by T. When the function is called with identity string, T is replaced with string, telling TypeScript to treat the argument and return type as a string. Thus, output is of type string. Classes in TypeScript. In TypeScript, classes are a foundational concept for object-oriented programming. They define blueprints for creating objects with specific properties and methods. Let's explore how to define a simple class. The code snippet defines a class called greeter with a property greeting, a constructor to initialize the property, and a method greet. The new keyword is used to create an instance of the greeter class, and we invoke the greet method to get the greeting message. Inheritance and abstract classes. Inheritance allows classes to extend from other classes, gaining access to their properties and methods. Abstract classes serve as base classes from which other classes may derive. They cannot be instantiated directly, but can define abstract methods and properties, which must be implemented by derived classes. In the code, the animal class is an abstract class that cannot be instantiated directly. It has an abstract method makeSound that any subclass is required to implement, indicating how the animal makes a sound. The move method is standard and can be used as provided. The snake class then derives from animal. It provides an implementation for the abstract method makeSound by overriding it with its own logic. Instances of snake can then be created and interacted with, whereas attempts to create an instance of animal would result in a compilation error. Interfaces versus classes. In TypeScript, interfaces and classes form the building blocks of object-oriented programming. An interface defines a contract that classes can implement, whereas a class is a blueprint for creating objects and can implement one or more interfaces. The code demonstrates interfaces and classes in TypeScript. The drawable interface defines a method draw without implementations. Circle and square classes implement the drawable interface by providing their own definitions of draw. An array of drawable is created, which can contain any object that satisfies the drawable interface. When we loop over the array and call draw on each object, it will call the appropriate method defined by the object's class. Implementing interfaces. In TypeScript, interfaces define contracts for classes, which can be implemented to ensure that the classes adhere to specific structures and behaviors. When a class implements an interface, it must provide an implementation for all the properties and methods declared by the interface. The code demonstrates how to implement an interface. iMessageSender is an interface with a method sendMessage that accepts a string. Classes emailSender and SMSSender each implement iMessageSender, providing concrete implementations of sendMessage. When invoking sendMessage through an instance of any of the implementing classes, TypeScript ensures that the method exists and can be safely called. Access modifiers: public, private, and protected. In TypeScript, classes can have attributes and methods with specific access modifiers. The three primary access modifiers are public, private, and protected. The public keyword allows access to the class member from anywhere. The private keyword restricts access to the class member from anywhere outside the containing class. The protected keyword is similar to private, but allows access within derived classes as well. In the provided code, person has a public property name, which can be accessed anywhere. The private property age can only be accessed within the person class, as seen in the getAge method. The protected property nickname can be accessed within person and the employee class, which extends person. The public greet method can be called on any instance of person, while attempting to call the private getAge method or access the private age property outside the person class will result in an error. The employee class can call the protected getNickname method because it is a subclass of person. Read-only and static properties. In TypeScript, read-only properties must be initialized at their declaration or in the constructor of the class. Once assigned, these properties cannot be altered. The user class has a read-only property called ID, which is set within the constructor and cannot be changed afterwards. Any attempt to modify ID after object creation will result in a compilation error, ensuring the property's value remains constant throughout the instance's lifetime. Getters/setters. Getters and setters are special methods that provide read and write access to an object's properties. TypeScript allows us to implement getters and setters to control the access and modification of the data. A getter is a method that reads or gets a property value, while a setter is a method that sets or updates the property's value, often with some sort of validation. In this code, we have a person class with a private age property. We provide a getter method age that allows external code to access the value of score age. Likewise, there's a setter method ageNewAge that allows us to change the value of age. The setter includes validation to ensure the age is positive before setting age to new age. If not, it logs an error. We instantiate a person object with an age of 25 and demonstrate getting and setting the age property. Understanding modules. In TypeScript, modules are a way to organize and encapsulate code. Each module can contain variables, functions, classes, interfaces, etc., which are not visible outside the module unless they are explicitly exported using the export keyword. You can include a module in another module using the import statement. Modules help in managing the code in a large application by dividing it into smaller, maintainable, and reusable pieces. The code defines a module named math module containing two functions, add and subtract, both exported for use in other modules. Other modules can import math module to use these functions. The export keyword makes them accessible outside the module scope. Without export, these functions would remain private to the math module. Exporting and importing modules. In TypeScript, modules are a way to organize code within a file. Each module can contain both declarations and logic. To use functions, classes, or constants across different files, you need to export them from the module where they are defined and import them in the module where you want to use them. In the code snippet, mathutils.ts defines a function named add that adds two numbers. This function is exported using the export keyword. Then, in main.ts, we import the add function from mathutils.ts using the import statement. This makes the add function available in main.ts, allowing us to call it and log the result. Default and named exports imports. In TypeScript, each module can export a single default export. This is useful for the primary functionality that is being exported. Default exports can be imported with any name you give them. In the file defaultexport.ts, the function sayHello is exported as the default export. In the main.ts file, this exported function is imported without the need to use curly braces and with a custom name greet. When greet Alice is called, it outputs hello Alice to the console. Working with namespaces. In TypeScript, namespaces are a way to organize code into named, logical groups and to prevent name clashes in the global scope. They are similar to modules but are not as powerful or flexible. Namespaces are defined with the namespace keyword followed by the namespace name. In the provided code, a namespace named myNamespace is defined, containing a class myClass with a method myMethod. The export keyword makes myClass accessible outside of the namespace. To use myClass, it is referenced with the namespace name followed by a dot as mynamespace.myClass. An instance of myClass is created and its myMethod is called, which logs a message to the console. Module resolution strategies. In TypeScript, modules are resolved according to certain strategies. The compiler provides two main resolution strategies, Classic and Node. The strategy used depends on the module system you target, such as CommonJS, AMD, UMD, or ES modules. By default, the Node resolution strategy is used when the module compiler option is set to CommonJS, UMD, AMD, ES6, or ESNext. Otherwise, the Classic strategy is used. The given code line attempts to import a module named myModule from a local file named mymodule.ts, or mymodule.tsx, or mymodule.dts, if ts is not found. Under the node resolution strategy, the compiler will look for the file mymodule.ts in the same directory as the importing file. If the file is not found directly, the compiler will try to find an index.ts inside a folder named mymodule. With Classic resolution, the compiler will not look into the mymodule folder for an index. Ambient modules. Ambient modules are used in TypeScript to describe the shape of modules provided by the global scope, especially when they are not provided as real TypeScript modules. This typically applies when working with existing JavaScript code and third-party libraries. They allow TypeScript to understand what the imports are and what types they entail without an actual TypeScript implementation. Here, we declare an ambient module for myLibrary. We don't define the actual implementation of doSomething, but we inform TypeScript that there is a function called doSomething available, which doesn't return anything, void. When you import myLibrary in a TypeScript file, TypeScript will use this declaration to understand the types being used without needing the actual library code to be written in TypeScript. Working with namespaces. Namespaces in TypeScript are a way to organize code into named scopes, preventing name collisions and organizing related features. The namespace keyword defines a new namespace named mathematics. Inside this namespace, we define a class calculator with a static method add. The export keyword makes the calculator class accessible outside the namespace. We invoke the add method on calculator using mathematics.calculator.add53 and log the result, which will be 8. Understanding modules. Modules are a core concept in TypeScript that allow you to organize and encapsulate code. Each module can contain both declarations and logic, separated from the global scope, which can be exported and imported by other modules. In this example, we begin by importing a function named sayHello from a local module file called greetings.ts. We then call the function with the argument world. The module system helps in managing the project's structure and dependencies. Exporting and importing modules. In TypeScript, modules are a way to organize and reuse code across files. When a module is created, its variables, functions, classes, interfaces, etc. are not accessible from the outside unless they are explicitly exported. The export keyword makes entities accessible to other modules. To use these entities in another module, the import keyword is used. Let's look at a simple example of exporting from one module and importing into another. In the code above, we have two files, mathutils.ts and calculator.ts. Mathutils.ts exports two functions, add and subtract, using the export keyword, making them available for use in other modules. Calculator.ts imports those functions with the import keyword by specifying the function's names in braces and the relative path to the mathutils module. It can then call the imported add and subtract functions and store the results. Default and named exports imports. In TypeScript, a module can export multiple entities, such as functions, classes, or variables. There are two types of exports: named exports, which allow multiple items to be exported from a single module, and default exports, which allow for a single item to be exported as the default from a module. In the provided code, two named exports, pi and calculate circumference, and one default export, circle class, are defined in a hypothetical math module. Named exports are explicitly listed and imported by their specific names within curly braces, whereas the default export is imported without curly braces, and its name can be chosen freely by the importer. Module resolution strategies. In TypeScript, module resolution is the process by which the compiler determines what an import refers to. There are two main resolution strategies, classic and node. The classic strategy is used in older codebases and the default for AMD modules, while node resolution strategy is commonly used in Node.js projects and is the default for CommonJS and ES6 module types. This import statement will trigger module resolution to locate my_module. With node resolution, TypeScript will look for my_module.ts, my_module.tsx, my_module.ds, then my_module/package.json to find a typings field, or my_module/index.ts, etc. Classic resolution is more straightforward. It travels upwards from the importing files directory looking for matching .ts files. Ambient declarations. Ambient declarations are used in TypeScript to declare the shapes of JavaScript objects that exist at runtime but may not be TypeScript aware. These declarations are typically used to describe the shape of third-party libraries or browser globals. The code defines an ambient variable, myLibrary. It tells TypeScript that myLibrary exists elsewhere and it's of type any. TypeScript will not check its existence or type during compilation. Configuring the TypeScript compiler. The TypeScript compiler is configured through a file named tsconfig.json. This configuration file specifies the root files and the compiler options needed to compile the project. The provided tsconfig.json example includes several key configurations. Target sets the ECMAScript target version for the output JavaScript files. Module defines the module system, here CommonJS. Strict enables a wide range of type-checking behavior for greater rigor. Outdir specifies the directory to output the transpiled JavaScript files. The include array determines which files are included in the compilation process, with /streg meaning all files within the sus directory. Using tsconfig.json. In TypeScript, tsconfig.json is a configuration file that specifies the root files and the compiler options required to compile the project. This file allows developers to tune the behavior of the TypeScript compiler to their desired settings. The tsconfig.json file can control a wide range of compiler settings, such as target JavaScript version, module resolution strategy, strict type checking options, and more. This configuration enables consistent builds across different environments and developers' machines. When the TypeScript compiler is run in a directory containing a tsconfig.json file, it uses that file to guide its process. Compiler options for strict typing. TypeScript provides several compiler flags that can be used to enable stricter type checking and catch potential issues at compile time. Setting strict to true enables a wide range of type checking behavior that makes TypeScript more stringent. No implicit any prevents variables and parameters from defaulting to any. Strict null checks enforces strict checking of null and undefined. Strict function types ensures correct typing of functions and the return types. Strict bind call apply enforces that the bind, call, and apply methods are used correctly according to their signature. Strict property initialization ensures that each property declared in a class gets initialized. No implicit this raises errors on this expressions with an implied any type. Always strict passes files in strict mode and emits use strict for each source file. Incremental compilation. Incremental compilation in TypeScript allows you to compile projects faster by reusing the previous compilation results. This technique only recompiles parts of the project that have changed, instead of rebuilding the entire project, which saves time, especially in large codebases. By running the TypeScript compiler with the flag nas_incremental, TypeScript generates .tsBuildInfo file, which stores information about the project graph from the last compilation. When you run the compiler again, it uses this information to detect which files have changed and need to be recompiled. The nash_p flag indicates which project configuration to use, in this case specified by tsconfig.json. This flag is often used in larger projects with complex configurations. Source maps for debugging. When TypeScript is transpiled to JavaScript, it can be hard to debug due to differences between the source and output files. Source maps solve this by creating a mapping file that links the transpiled code back to the original TypeScript files, allowing developers to debug their original TypeScript code directly in the browser or in their editor. By setting the source map option to true in the compiler options of your tsconfig.json file, when the TypeScript compiler runs, it produces source map files with a .js.map extension alongside the compiled JavaScript files. These .js.map files provide a mapping back to the original TypeScript files, which enables debugging tools to interact with the original TypeScript code rather than the transpiled JavaScript. Linting TypeScript with tslint, ESLint. Linting is an important aspect of modern web development. It helps to maintain code quality and consistency by detecting errors and potential problems in the early stages. While tslint was the mainstream linting tool for TypeScript for a long time, it has been deprecated in favor of ESLint, which now has robust TypeScript support. Below is an example of setting up ESLint in a TypeScript project. This npm command installs ESLint, the TypeScript parser, and the TypeScript ESLint plugin as development dependencies. The parser allows ESLint to understand TypeScript syntax, and the plugin provides TypeScript-specific rules and extends ESLint's capabilities. Introduction to declaration files. In TypeScript, a declaration file is a file that doesn't contain any concrete implementation, but rather specifies types for code that exists elsewhere. The above code is an example of a simple declaration file for a fictional sum library. It tells TypeScript that there is a module called sumLibrary that has a function doSomething, which accepts a string argument and does not return anything. The declare keyword is used to define ambient declarations where you want to describe a type without providing an implementation. Understanding .des files. In TypeScript, DES files are used to provide type information about an API that's written in JavaScript. They describe the shape of an object, allowing TypeScript to understand how the object can be interacted with. This allows developers to use existing JavaScript libraries in TypeScript applications, without TypeScript generating any actual JavaScript from these files. This code illustrates a basic declaration file, which declares a module, myLibrary, with a single function, myFunction. The function is expected to take in a string argument and return a string. By using declare, We inform TypeScript that this module exists and provide the necessary type information, but we do not create any runtime JavaScript code. Writing your own declaration files. When working with JavaScript libraries or your own custom JavaScript code in a TypeScript project, you will sometimes need to write your own declaration files. This is necessary when the library does not include its own TypeScript declarations, and there is no available @types package with the declarations. In the provided code, we declare a module named my_library, which represents a custom or third-party JavaScript library. Inside the module, we use the export keyword to expose a function myFunction, a constant myConstant, and an interface myInterface to be consumed by TypeScript code. The myFunction takes a number as its argument and returns a string. myConstant is of type number, and myInterface defines a structure for objects with a property name of type string. This declaration allows TypeScript to understand the shape of myLibrary and provide type checking and IntelliSense in IDEs when using this library. Third-party declaration files. In TypeScript, when working with third-party libraries, declaration files .ts are important for providing type information about the library's public API to the compiler. Such files do not contain implementation details, but only type annotations. If a library does not include its own type declarations, you can usually find them in the definitely typed repository or install them using npm. The command provided is an npm command used in Node.js. It installs the declaration files for the Lodash library. These files are not written by Lodash's authors, but by contributors to the definitely typed repository. After running this command, TypeScript will be able to understand the types and APIs provided by Lodash, assuming you are using the library in your TypeScript project. This allows your code to be type-checked for correctness when using Lodash functions. @types package and definitely typed. When working with TypeScript and third-party JavaScript libraries, type definitions are essential so that TypeScript can understand the types being used. Not all libraries are written in TypeScript, hence they don't provide their own type definitions. That's where Definitely Typed, a community-led project, comes in. It hosts type definitions for a wide range of JavaScript libraries. The @types packages are the npm packages that contain the type definitions from Definitely Typed. The command in the code section is an example of how to install type definitions for the Lodash library using npm. When you run this command, npm searches for a package named @type/lodash in the npm registry, downloads it, and adds it to your project's node modules directory, as well as to your dev dependencies in package.json. This allows TypeScript to use the types defined in this package to type check your code where Lodash is used, without having to manually write type definitions. TypeScript with React. When using TypeScript with React, you define components with either function or class syntax, using typed props and state. Here's how you define a functional component with typed props. In this example, we have imported React and defined an interface props that specifies the structure of the props our functional component will accept, in this case, a single title prop of type string. The myComponent function is then typed with react.fcprops, which is a generic type provided by the React type definitions to denote a function component that accepts props of the specified type. The component returns a JSX element that displays the title prop. TypeScript with Angular. Angular is a popular front-end framework that is built to use TypeScript. By default, Angular applications are meant to be developed with TypeScript, leveraging its features for type safety and modern JavaScript features. Setting up an Angular project automatically configures TypeScript. This code defines an Angular component using TypeScript. The @component decorator is used to annotate the class appComponent, telling Angular details about the component, such as its HTML selector, the URL of its template, and the location of its specific styles. The title property is of type string, which can be bound to the template for display. TypeScript's type checking confirms at compile time that title is used correctly within the component, enforcing type safety and reducing the risk of runtime errors. TypeScript with Vue.js. Vue.js is a popular front-end framework, and it supports TypeScript out of the box from version 2.5. Using TypeScript with Vue.js enhances code quality and developer productivity. Let's see how to define a Vue component with TypeScript. In the code snippet above, we use the Vue property decorator library, which provides decorators to create Vue components with TypeScript classes. We declare a component class Hello World that extends Vue, and use the @component decorator to denote that it's a Vue component. Inside the class, we define a data property, greetMessage, typed as a string, and initialize it with a greeting message. The template section of the Vue component uses this data property to render the greeting message. Component props and state with TypeScript. In React, components receive immutable data from their parents through props and maintain their own mutable data called state. TypeScript enhances these aspects by adding strong types. For props, we define an interface or type. For state, we can either use interfaces or directly pass the state shape to the state hook, useState. Below is an example using a functional component with TypeScript. In the given code, the counter component is a functional component that expects initial count as a prop. The type iProps is an interface defining this requirement. The component keeps track of its own state using the useState hook. The state count is strictly typed as a number. On clicking the button, the count state is incremented, demonstrating both the use and flow of props and state in a strongly typed manner with TypeScript. Hooks and context in TypeScript. React hooks allow you to use state and other React features without writing a class. Context provides a way to pass data through the component tree without having to pass props down manually at every level. In TypeScript, using hooks and context involves typing the initial state, context values, and the return values of the hooks for enhanced type safety. This code snippet defines a user interface to shape the data structure, creates a user context using React's createContext tailored for a user object, and sets the default value to undefined for cases where it may not be provided. The user provider component uses the useState hook to manage the user state and provides it through userContext.provider. A custom hook useUser is defined to ensure that the context is consumed only within a user provider context. Lastly, there's a user profile component demonstrating the usage of the useUser hook, which safely retrieves the user data from context. Setting up a TypeScript Node.js project. To set up a TypeScript project for Node.js, you must configure TypeScript to work within the Node.js environment. This involves initializing a new Node.js project, installing TypeScript, and configuring the TypeScript compiler. The commands npm init-y initializes a new Node.js project by creating a package.json file with default values. npm install TypeScript tsnode at types node-save dev installs TypeScript, the TypeScript Node.js execution environment, and type definitions for Node.js as development dependencies. Finally, tsc init creates a tsconfig.json file, which is used to configure TypeScript compiler options for your project. Using TypeScript with Express.js. When using TypeScript with Node.js and Express, it's important to set up the compiler options correctly. You'll typically need to install types for Node and Express, and you might want to use tsnode for easier execution during development. Here is an example of how to initialize a basic Express server using TypeScript. This code snippet shows the setup of a basic Express server in TypeScript. The Express module is imported at the top, and an instance of an Express app is created. We define a get_route to the root / that responds with Hello World. The app starts listening on a specified port, and a message is logged to the console when the server is running. To execute this, make sure you have Express and @types_express installed, tsnode for running TypeScript directly, and a tsconfig.json file configured for your project. Creating API routes with TypeScript. When using TypeScript with Node.js and Express, creating API routes involves defining route handlers with type annotations to take advantage of TypeScript's compile time checks. Let's create an API route that handles a GET request and returns a simple message. In the provided code, we import the Express module along with request and response types to define the shape of the request and response objects. A GetRoute /hello is defined, which uses a handler function with rec and res parameters typed as request and response. The handler function sends a JSON object with a welcome message. Finally, the the Express application listens on port 3000. By adding types, we ensure that we adhere to the correct structure and properties when handling requests and responses. Connecting to a database with TypeScript. To connect to a database with TypeScript in a Node.js and Express application, you can use various client libraries depending on the type of database you are connecting to. For example, if you're connecting to a MySQL database, you might use the MySQL npm package, whereas for MongoDB, you might use Mongoose. In this example, we will use the PG package to connect to a PostgreSQL database. The code sample demonstrates how to set up a connection pool to a PostgreSQL database using the PG package. A pool is created with configuration parameters such as the username, host, database name, password, and port. These should be updated with the actual values needed to connect to your specific PostgreSQL instance. The query function is defined and exported to abstract query execution. It takes a text string containing the SQL query and an optional array params for parameterized queries. The pool.query method is then called with these arguments to execute queries against the database. Middlewares and error handling with TypeScript. In Node.js with Express, middleware functions are those that have access to the request object, requeue, the response object, res, and the next middleware function in the application's request-response cycle. Middlewares can perform various tasks such as executing code, making changes to the request and the response objects, ending the request-response cycle, or calling the next middleware in the stack. The code defines a custom middleware function, myMiddleware, that simply prints middleware triggered to the console and then calls the next function to pass control to the next middleware in the stack. The middleware is applied globally to all routes by using app.use. When a GET request is made to the root / the middleware is executed before the response is sent. Utility types. The partial utility type constructs a type with all the properties of an existing type set to optional. It's extremely helpful when you want to create objects based on some existing type, but only with a few properties. The updateToDo function takes a to-do object and an object with a subset of todo properties. We use the partial utility type to indicate that fields to update can have any combination of properties from to-do, but none of them are required. The function returns a new object that has all the original to-do's properties and the updated ones, showcasing how partial helps in updating subsets of object properties. Keyof and typeof operators. The keyof operator takes an object type and produces a string or numeric literal union of its keys. In the example, person keys is a type that is equivalent to the union of string literals name and age, which are the keys of the person interface. This is useful for creating types that are limited to the keys of an object. Indexed access types. Indexed access types in TypeScript allow you to access the type of a property of another type. It uses an index type query like type, key type, to look up a specific property on another type. In this code snippet, an indexed access type is used to declare person name as the type of the name property within the person type. The person name type is therefore equivalent to string. The greet function shows that name is correctly typed as person name, allowing the function to access person.name without type errors. Conditional types. Conditional types help us to express non-uniform type mappings, where the type to be returned depends on a condition. A conditional type selects one of two possible types based on a condition expressed as a type relationship test. Here, we have defined a utility type non-nullable, which takes a type T and returns never if T is null or undefined. Otherwise, it returns T. This uses the TypeScript ternary syntax. T extends U, X, Y, which can be read as, if T is assignable to U, the type is X, otherwise the type is Y. Decorators. Decorators are a special kind of declaration that can be attached to a class declaration, method, accessor, property, or parameter. Decorators use the form @expression, where expression must evaluate to a function that will be called at runtime with information about the decorated declaration. In the provided code example, the sealed function is a decorator that seals both the constructor and its prototype, preventing new properties from being added to them. When the @sealed decorator is applied to the greeter class, it is invoked automatically, ensuring that the greeter class cannot be extended with new properties at runtime. This demonstrates the use of decorators to alter or augment class behavior at design time. Decorator factories. Decorator factories are a way to create decorators that can accept parameters and customize their behavior. Instead of writing the decorator itself, you write a function that returns the decorator function. This allows you to configure your decorator when you apply it. In the example, color is a decorator factory that takes a value parameter. This factory returns a function, which is the actual decorator that will be applied to the target, e.g., a class or method. When using @colorBlue, you're invoking the factory with blue as an argument, which then returns the decorator function customized with the blue color that can be used to add metadata or behavior associated with that color to the class. Unit testing with Jest. Jest is a delightful JavaScript testing framework with a focus on simplicity. It works with projects using Babel, TypeScript, Node.js, React, Angular, and more. It's often used for writing and running unit tests for TypeScript projects. To start, you'll need to install Jest using npm or yarn and configure it to transpile TypeScript code using tsJest. The provided code sample is a basic Jest test for a TypeScript function named sum. The test function defines a new test case, where it expects that the sum function, when called with arguments 1 and 2, returns 3. The expect function is used to assert that the result of sum1,2 matches the expected output, which is 3, using the .2b matcher. If the function behaves as expected, the test will pass. Otherwise, it fails, indicating a potential bug in the implementation. End-to-end testing with Cypress. Cypress is a front-end testing tool built for the modern web. It allows you to write end-to-end tests in JavaScript or TypeScript. This testing method simulates real user interactions with your application, ensuring that the entire system functions correctly from start to finish. A typical Cypress test might involve visiting a web page, interacting with elements, and asserting that the expected behavior occurs. In the provided code, describe is a Cypress command used to group related tests together, and it is a command that represents a single test. The example test first visits the login page with cy.visit/login, then types a username and password into the respective fields with cy.get, type, submits the form, and finally asserts that after submitting, the URL should include /dashboard to confirm that the login was successful. Integration testing. Integration testing assesses how different parts of an application work together, such as testing interactions with a database or ensuring that various services communicate properly. In TypeScript, you can use testing frameworks like Jest or Mocha with additional modules like supertest for HTTP assertions to create integration tests. In the code provided, we use the supertest library to perform an HTTP GET request to the /AP items endpoint of our application, which is imported as app. Within the describe block, we have an asynchronous test case that sends a request and uses expect to assert that the response status is 200, indicating a successful request, and that the body contains an array, which we expect to be the list of items. This is an example of an integration test because it tests the endpoint in the context of the running application, but it does not mock or isolate individual units of code. Mocking and testing utilities. In testing, mocking is a technique that allows you to simulate the behavior of real objects or modules to ensure your tests have control over external dependencies. TypeScript, being a superset of JavaScript, can take advantage of JS testing libraries such as Jest or Sign-On to create mocks, spies, and stubs. Testing utilities help to isolate the code you want to test, provide mock implementations, and assert that the code behaves as expected. In this code example, we use Jest's mocking utilities to override the implementation of my function imported from my module. We set up a mock function using jest.fn and define a mock implementation that returns the string test value. In our test, we assert that calling my function returns the mocked value test value, ensuring that our test does not rely on the actual implementation of my function. This is useful for testing pieces of a system in isolation without the need for the actual dependencies to be in place. Testing TypeScript in the front end. To test TypeScript in the front end, we start by setting up a testing environment that's capable of handling TypeScript syntax. A common setup involves using Jest as the testing framework together with a transpiler like tsjest to handle TypeScript code. The commands install Jest and tsjest, which are the testing framework, and a TypeScript preprocessor for Jest respectively, as well as the types for Jest. The second command initializes the configuration file for tsjest. Testing TypeScript in the backend. Testing is a critical part of backend development to ensure the application works as expected. For a TypeScript backend, it generally involves setting up a testing framework compatible with TypeScript, writing test cases, running them, and analyzing the results. This code snippet is a command to set up Jest, a popular JavaScript testing framework, with TypeScript support in your backend project. tsjest is a preprocessor that compiles TypeScript code for Jest, and @typesjest is a type declaration package providing TypeScript types for Jest. Project references. Project references in TypeScript are a way to structure your TypeScript projects into smaller, interdependent blocks. This can improve build times and enforce logical separation between different parts of your application. For example, you might have a core library and a consuming app. Instead of building the entire codebase at once, you can build them separately, and the consuming app can use the already compiled output of the library. In the example, tsconfig.library.json is configured with the composite option set to true, allowing it to be referenced by other projects. It's important because it signals to TypeScript that this project is intended to be built with other projects. The outdir is set to libdist, which specifies where the output files should be generated. Then, in tsconfig.app.json, we set up a project reference using the references array. This points to the library project's config file, allowing TypeScript to recognize the dependency and use the library's compiled code when building the app project. Build and watch modes. In TypeScript, build mode refers to the process of compiling TypeScript files into JavaScript. Watch mode enables TypeScript to automatically watch for changes in your files and recompile them as needed. The nas build, or -b flag with the TypeScript compiler, TSC, initiates the compilation of TypeScript code into JavaScript. It is useful when you have multiple configurations or a project references set up. The nas watch, or W, flag starts TypeScript in watch mode, where it monitors your source files for changes and recompiles them whenever it detects a change. This is useful during development, as it provides immediate feedback on code changes without the need for manual recompilation. Code organization and best practices. In TypeScript, as in any language, organizing your code effectively is crucial for readability, maintainability, and scalability. Here, we adhere to some of the best practices for organizing TypeScript code, including consistent file naming, modularization, and proper use of types and interfaces. In the provided code snippet, we define an user interface and a user service class. By exporting them, we keep related pieces of code encapsulated in a single module, promote reusability, and maintain separation of concerns. The file is named example.ts, which should be more descriptive in a real project to reflect its purpose. The interface dictates the shape of user data, while the class offers functionality related to users. Performance optimization. In TypeScript, performance optimization is about writing code that not only fulfills its functional requirements, but also executes efficiently. This can encompass optimizing compile time performance for faster builds, and runtime performance for efficient memory and execution time usage. The provided code is simple, yet there are opportunities for performance optimization. To optimize, we could avoid creating a new instance of point every time add points is called. Instead, directly operate and possibly mutate an existing instance if immutability is not a concern. This reduces garbage collector overhead by reducing the number of objects created. Debugging TypeScript. Debugging is a critical skill for developers. For TypeScript, debugging can seem a bit challenging at first, because TypeScript is transpiled to JavaScript, which is what actually runs in the browser or on the server. However, tools like source maps enable us to debug our TypeScript code directly. The provided code is a simple TypeScript statement that prints a message to the console. When debugging, a developer could set a breakpoint on this line if running the code within an IDE or browser's development tools that support TypeScript source maps. This would allow the execution to pause, and variables or call stacks can then be inspected. Monorepos with TypeScript. A monorepo refers to a single repository containing multiple codebases that might be related or interdependent. This is often used to simplify dependency management, streamline workflows, and promote code sharing. In TypeScript, a monorepo can help manage types and interfaces across projects effectively. There isn't a specific code example for the concept of monorepos, as it is a project structure strategy rather than a code construct. In TypeScript projects, this could be implemented using tools like Learner for managing packages or Yarn workspaces for handling dependencies. Each package within the monorepo could have its own tsconfig.json file for TypeScript compilation options, and shared types could be placed in a common directory accessible to all packages. Advanced type mapping. Type mapping in TypeScript allows you to transform types in a type-safe way. This can be particularly useful when you want to create new types based on existing ones with some modifications. The Mapped Types feature gives you the ability to iterate over the keys of an object type and to transform them into other types. Let's explore how to create a mapped type that makes all properties of an object type read-only. In the code snippet above, we define a generic read-only type. It uses a mapped type to iterate over all the keys k of the type t passed to read-only. For each key, it creates a new property with the same key and type, but adds the read-only modifier, effectively making all properties of the resulting type immutable. The user interface is then used to create a new read-only user type, where both ID and name are read-only, preventing assignment after their initial declaration. Building a REST API with TypeScript and Node.js. To build a REST API with TypeScript and Node.js, we use frameworks like Express.js. First, ensure Node.js is installed, then initialize a project with npm and install TypeScript along with Express and its type definitions. We then set up TypeScript compilation and define our Express server and API routes. The provided code snippet demonstrates the basics of setting up an Express.js server with TypeScript. It imports necessary modules and types, initializes an Express application, uses middleware to pass JSON request bodies, defines a GET route to respond with a greeting message, and starts the server on a specified port, logging a message to the console once the server is running. Creating a web frontend with TypeScript and a framework, React, Angular, Vue. React is a popular JavaScript library for building user interfaces. TypeScript can be used with React to enforce type safety, which helps in managing the state and props in components with better compile time validation. We'll create a simple React component in TypeScript to display a greeting message. In this code, we import React and define a functional component named greeting. The interface greeting props declares the shape of the props that the greeting component will accept, which in this case is an object with a name property of type string. The component takes the name from its props and renders it inside a div tag. Finally, we export the greeting component for use in other parts of the application. TypeScript with serverless and AWS. Using TypeScript with serverless on AWS allows developers to build and deploy scalable applications by writing type-safe code and leveraging AWS services without managing servers. The AWS Serverless Application Model, SAM, is often used in conjunction with the serverless framework for deploying serverless applications. The provided code represents a simple AWS Lambda function written in TypeScript. It imports types for the API Gateway event and result objects from the AWS Lambda package. The handler function is async and takes an API Gateway proxy event object as its input. It returns a promise that resolves to an API Gateway proxy result, which includes the HTTP status code and a body containing a JSON string. When deployed, this Lambda could be triggered by AWS API Gateway to provide a serverless endpoint. Creating command line tools with TypeScript. Command line tools are essential for automating tasks in development workflows. TypeScript can be used to write maintainable and robust CLI tools, leveraging Node.js. We are going to create a simple TypeScript command line tool that prints a message provided as an argument. The code snippet begins by importing the necessary modules. The yargs library is used to pass command line arguments, which makes handling input much easier. Process.argv.slice2 is used to remove the first two elements of the process argv array, which contain the node executable and file path, to only get the arguments passed by the user. The argv.message is an example argument we expect, which if provided, will be printed to the console. If no message is provided, the script prints an error and exits with a status code of 1, indicating a failure. Publishing and managing TypeScript libraries. Publishing and managing TypeScript libraries involves compiling TypeScript code to JavaScript, including type definitions for consumers, and packaging it for distribution through package managers like npm. It is crucial to consider aspects like versioning, documentation, and compatibility. The npm publish command is used to publish your TypeScript library to the npm registry. Before running this command, you should compile your TS files to JS and generate type declarations. Ensure that main in package.json points to the entry JavaScript file, and types points to the main declaration file. Contributing to definitely typed. Definitely typed is a repository of type definitions for JavaScript libraries that do not provide their own TypeScript declarations. When contributing to definitely typed, the goal is to provide accurate type information for JavaScript libraries to enhance TypeScript developer experience. This topic involves no specific code example, as it is an explanation of a process rather than a code snippet. Contributing to definitely typed typically involves creating or updating a types folder containing the declaration files .dts for the JavaScript library in question. The contribution process includes forking the definitely typed repo, making changes, running tests to ensure correctness, and then submitting a pull request for review by the community.